Okay, so now, as anticipated, we venture a bit in a weird territory, let's say. The first way in which, at least from the perspective of these lectures, this territory is a bit weird is that here we are actually at the very border between data science and artificial intelligence. So, for instance, this bunch of slides could be could belong to the first to the other half of the course, okay, to Professor Monica part, to the AI part. That would be perfectly fine. So we really are at the border. First, let's say weirdness. Second weirdness is, as I anticipated, this is, let's say, a third category of machine learning. So we had supervised learning, unsupervised learning. This is a different category. And we will highlight what the main differences are. By chance, this is also one of my main research interests. So let's say that if you're interested in doing any project or thesis or internship in every topic in my lectures, you're fine. On this topic, we are doing actively our research activities. So this is roughly the outline. Obviously, we won't see everything today. It will take us a few lessons. I forgot the third, probably, source of weirdness of this part. As you can notice, the slides are different, basically because different versions of this material are used by me here in the artificial intelligence master degree in Modena and in PhD courses. Obviously, they are slightly different, but the basic shell is the same. And so, since I'm lazy, I didn't redo the whole layout of the slides. So that's the only reason why these are different. So basically, we will talk a bit about the basics of reinforcement learning. And for reinforcement learning, I mean, we will define reinforcement learning, but basically, I mean a scenario in which there is one entity that must learn. This thing is completely new for us. I mean, when we talked about supervised learning or unsupervised learning, there was always one entity learning, the software program training the model and maybe deploying the model at runtime. Here, instead, we will quickly transition to a world in which there are multiple multi-agent reinforcement learning. The one that learns in this field of research is called an agent. And we will quickly transition from single agent reinforcement learning to multi-agent reinforcement learning. And the motivation is simply that my main research interest is in multi-agent reinforcement learning. It is also newer. Reinforcement learning exists since a lot of time. It is still newer than supervised and unsupervised learning. It is still not very well established in the industry, for instance, compared to supervised learning and unsupervised learning that are used extensively, okay? Reinforcement learning is still more of a niche application in the industry. Most applications of reinforcement learning to date are video games. So the AI of the video game usually has been partly programmed, partly trained with reinforcement learning. Robotics, and one that probably is unsuspected, recommendation systems, which are something that you may never heard of probably, but it's basically those kind of systems such as Amazon, who bought this, also bought that, such as Netflix, since you watched this, also watch that. And one probably unsuspectable one is finance. Most of trading in finance is done automatically by reinforcement learning trained algorithms. So there are applications. They are not yet so pervasive as supervised learning and whatever. So basically, we will start from the very basics of reinforcement learning and then try to quickly go in a more difficult world, okay, that is the world of multi-agent reinforcement learning. So in its essence, reinforcement learning is extremely easy. The core idea is extremely easy and quite familiar. So we have an agent, an entity, okay? It's called agent because the entity has the possibility to act on an environment. It can be a virtual environment. It could be completely a digital environment, like, I don't know, modifying the rows in a database. It doesn't need to be a physical environment. Oftentimes, reinforcement learning is meant to be deployed in a physical environment, but not always. For instance, in video games, in trading, the environment is the virtual environment of the video game. In trading, the environment is all of the properties of the trading dynamics, the opening price, closing price, trading volumes, whatever. Okay, so it must not be a physical environment. We have an agent, and we already see in this very definition, in this basic definition, the first big difference with both supervised and unsupervised learning. The agent can act in the environment. What does it mean? It can carry out actions that modify the environment. This is completely new. In supervised learning, the agent, let's imagine that the agent in that case is the software application that has been trained or is training to do some prediction, to do some classification, is not doing any action on the environment that it used to learn. The environment in that case is a dataset, static dataset, that's it. You learn, you don't take any action on the dataset. You don't modify the dataset, sorry. Your only action is a prediction. You never modify the environment. The same happens for clustering, for unsupervised learning in general. You never modify, your environment is your dataset, you never modify the dataset. You look at the dataset and do something else. Do we agree? Here instead we have an environment, physical, virtual, mixed, we don't care, and the agent can affect the environment, can change it. A robot can pick up an item or move an object or move itself in the environment. The agent wants to achieve a goal, wants to carry out a task. Okay, let's assume a video game in which the player, the agent of the player, must reach the exit of a maze. Okay, so the agent has a task, must learn to do a task, exit from the maze. Okay, be the first in a car racing game. A robot must learn to pick up a specific item. Okay. So the goal is basically a desired state of the environment. Okay, could be the player at the exit position, could be the robot holding the object in a robotic hand. Okay, stuff like that. Is a state of the environment, all the properties that describe the environment and the agent, that corresponds to the position, to the final state we wanted to achieve from any given initial state. So the basic idea is that the agent acts in this environment and gets rewards, okay, based on its actions. Obviously, positive rewards if the actions are good, negative rewards if the actions are bad. So why there is a picture of a dog here? Because this should basically be familiar, because this is more or less the way you train a dog to do something, okay? Or in general an animal, or I would say in general toddlers, okay? You try to make them understand what's the task you want them to accomplish. So, in the example of a dog, the dog is the agent, because he is the one who trains, okay? And probably us, okay, the instructor, are the dog environment. Why? Because we are the one that gives, for instance, the reward to the dog. We are the one that speaks to the dog to give the command alert, or that we do gestures, okay, corresponding to the behavior, the task that the dog should learn. So for instance, I want to train the dog to bring back the stick, so I throw a stick, the dog does nothing, or goes and starts to bite the stick randomly, okay. Basically, probably after a while, the dog will, by chance, bring the stick back to me. And then I must be ready and give him a prize. Okay? Fine. After a few tries, probably the dog starts recognizing that every time I throw the stick and he fetches the stick and brings it back to me, he gets a prize. After a while of trial and error and repetition of the same and different actions, blah, 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 probably the dog would have learned that anytime I throw a stick, I want the stick back. And this is basically how reinforcement learning works. The agent takes actions. In this case, the dog goes and fetches the stick. Okay. Based on this action, the agent may get a reward. If the dog goes and bites the sticks and comes back with nothing, there is no reward. There could even be a negative reward, so a punishment. Okay, but we don't want to eat the dog, so that's for another example. So basically, in reinforcement learning, there are always these two entities, the agent and the environment, that interact in this way. The environment gives to the agent observations and rewards. What are observations? Well, the state of the environment. I throw the stick, the dog must be able to see me throwing the stick, must be able to see where the stick ends up being. That's the state of the environment, okay? In a maze, in a video game, the state of the environment is where are the walls, where are the free paths, where is the exit position, where is the starting position, what is my position, the position of the agent that has to exit the labyrinth, the maze, okay? And a reward, as we said, depending on the specific state of the environment, okay, and the action that the agent did, the agent may get a positive or negative reward. It is not necessary that at every action corresponds a reward. As I said, since the dog, until the dog doesn't bring me back the stick, it gets no reward whatsoever. So it is not necessary. So one flow of information is from the environment to the agent, and comprises the observation of the state of the environment and a reward, possibly a reward. The other flow of information is the opposite, flows from the agent to the environment, and that's the action. Okay. How did the agent modify the environment? In the case of the dog moved. The dog fetched the stick. The dog brought the stick back. Okay, many different actions that change the state of the environment. The stick was there, now the stick is in the mouth of the dog, or now the stick is nearer because the dog is bringing the stick. Okay. So the whole idea of reinforcement learning, as we said, is that by acting repeatedly and by receiving rewards, again, not necessarily always, but from time to time, the agent learns an optimal behavior. Ideally, the behavior is optimal. Okay? In general, it learns a behavior. In the jargon of reinforcement learning, this behavior is called a policy. I don't know if you're familiar, because I don't know by memory your plan of study, but if you took some lectures on game theory, this will be a strategy. In game theory, this is the exact same thing, but it's called a strategy. Usually we can distinguish between a problem, an environment with dense rewards, if the reward is given to the agent at every action, basically. Okay, it's dense. The agent gets many rewards. Okay, one example could be our video game with the goal of exiting a maze. The agent gets a reward every time he does an action. And the reward could be how closer you are to the exit with respect to the previous step. After every action, I can give that reward. I can compute the distance. On the contrary, a sparse reward is only when the goal is achieved. So in the case of the maze, will be the agent doesn't get any reward until it reaches the exit. More similar to the dog case. Until the dog brings back the stick, there is no reward. Obviously, you can have situations in between these two extremes, okay? So dense reward after every action, sparse reward only when the task is completed. You can have a gray area in between. So only specific actions give you a reward. Not every action, not only the achievement of the goal, but some specific. These are two extremes. So basically, we can even interpret this agent as being nothing different as our machine learning algorithm. There is an algorithm that gets as input the observations and the rewards and outputs an optimal, hopefully optimal policy. A policy is simply an association, a map between the state of the world and the action that I want to do in that state. A simple function, okay? It's a mapping between I see this state, the stick is there, my action is go fetch the stick. That's a policy. You can even imagine a policy in its most simple terms as a huge collection of if-then-else statements. Okay? If this is the state, do that. If this is the state, do that. Obviously, this is not the case if the problem is complex, because you cannot enumerate all of the possibilities. You can imagine conceptually the policy as being this mapping. So this is the very basic idea of reinforcement learning. A problem of reinforcement learning. So the problem of learning a policy with this method usually needs two ingredients. One, we already mentioned it, is the environment, essentially, which in slightly more general terms is usually called the decision process model. Why decision process? Basically, the environment must be specified, must have a specification that dictates how the environment transitions from state to state depending on the action of the agent. That's why it's called a decision process model. Depending on the decision of the agent, the action it made, the environment changes. Okay? So besides this decision process model that basically formally defines the interaction, the dynamics between the agent and the environment, obviously the other ingredient is what is the goal of learning. What do we want to learn in this problem? So let's focus on these two things. Let's define these two things. So the decision process model can be different from environment to environment. What does it mean can be different? It can have different constraints, it can have different requirements, it can have different assumptions. For instance, the decision process model in general establishes how the environment, as we said, works in terms of how the environment transitions between states depending on the action of the agent. To make this more concrete and why we can have different decision process models, let's mention two widely known decision process models. The most basic one is the MDP. You may have heard of MDPs even outside of reinforcement learning because they are not exclusive of reinforcement learning. In game theory, in optimization, reinforcement learning actually is an optimization technique. Okay, so if you studied operations research, optimization courses, probably you studied, let's say, traditional solutions in the sense you didn't involve machine learning. So there were algorithms invented, implemented by researchers, and these algorithms are programmed to work in a given way. Reinforcement learning is a different technique to solve optimization problems because you want an optimal policy. Okay? So the MDP, Markov decision process, is simply a decision process in which the current reward, so the reward that at any given step the agent gets, and the future state in which the environment will transition depending on the action, does not depend on the whole history of actions of the agent. They only depend on the current state. This is something that exists well beyond reinforcement learning, okay? So the Markov property is the memoryless property that I'm sure you heard of in many different exams, okay? So if I want to get to the exit of the maze, I don't really care about all the sequence of steps I took in the past, so all the movement decisions I made to be in a given position. To understand whether the given position is good or bad, I don't care. I mean, am I close to the exit? It's good. Am I farther away? It's bad. So, and to decide my next move, I don't care about what I did in the past. If I have a wall on my left, I don't want to go crashing into the wall. It doesn't matter how I get in the position of having the wall on the left. That's the Markov decision process. The most basic kind of environment you may have in reinforcement learning. Another example could be instead what is called a PONDP, so a partially observable Markov decision process. The only difference between the two is that in a Markov decision process, the agent can perfectly observe the environment. It means that when the agent observes the environment, so let's say when we give to the agent the observation, the data that it needs to learn from, the data is all I know about the environment. It could be, for instance, in the case of the maze, the video game, the agent knows the coordinate of the exit, it knows its own absolute coordinates, okay, and it knows the coordinates of the walls. The state of the environment is completely known to the agent. Again, just in case you are familiar with it, in the world of game theory, this will be a perfect information game, and anybody knows everything. In a PONDP, partially observable, as the name suggests, the agent does not know the exact state of the environment. It only gets an observation that may be less than the complete state in two ways. Either it is a partial view of the state, the same example of the maze environment. I don't have all the information I mentioned before. The only information I have is my nearby tiles. 1 meter, a sphere of 1 meter around me. I can see only there. The rest is black, is obscure. I cannot see. There is fog, whatever you want. That will be partial in observability in the sense that the whole state is not visible to me. Only part of the state is visible, my surroundings. You think about robotics application, that's usually the case. A robot may use a visual system with a camera, may use lidars, may use ultrasonic sound, something, but it cannot completely perceive the state of the environment. Okay, the camera has a certain depth and a certain field of view. The lidars also are rays that you cast and that cannot completely scan the whole space. So that's usually the most common situation. However, there is another notion of partial observability that does not necessarily regard I can only see a subset of the state features, but maybe I can see all of the state features, but I can see them, I can be informed about them through sensors, a camera, a leader, a temperature sensor, a motion sensor, whatever, that may make errors, or that may have noise. Okay? That's another notion of partial observability. So I can observe everything, but with some uncertainty. I'm not really sure that the temperature is 17 degrees. Maybe it's 17 and a half. Okay? And obviously you can combine the two. You can have partial observability because you cannot see all the environment, and what you can see can also contain errors. So these are just two examples. Afterwards, we will see others of uh, assumptions that we make when we define a decision process. Why should I care about this sort of stuff? Well, if you have a specific problem from the real world, an optimization problem, you tried to apply traditional optimization techniques if you can, but they failed. Maybe because they took too much time, maybe because the situation was suboptimal, okay, something, stuff like that. You want to try reinforcement learning. You model your environment, okay, so you model the transitions in the environment, the action that the agent can make, you model the observation that you give to the agent, stuff like that. Then, before applying algorithm, okay, reinforcement learning algorithm, usually you must know in which category your environment falls. Because, for instance, the guarantees of of learning the optimal policy, or the likelihood, if not guarantee, that your learning algorithm works well, obviously depend on these properties. So that's why it makes sense to have these categories of environment. Certain algorithms work well here, certain algorithms work well here, stuff like that. That's for the first half of the problem, so the environment and its relationship with the agent, the decision process model. The second half, in single agent reinforcement learning, so when there is only one dog that I'm training, it's extremely easy. The learning goal is always the same. Maximizing the expected return. What does it mean? The accumulated rewards during my lifetime. That's always the same. The optimization goal is always the same. The agent learns simply by trying to accumulate the most rewards it can before reaching the goal. So in single agent reinforcement learning, we don't need to define the learning goal. Learning goal is all from the perspective of the learning algorithm, okay, is always the same. Maximize the expected return. Okay. Obviously, this is from the perspective of the learning algorithm. In our different environments or problems, the actual goal will be different. In the maze example, the goal is to exit the maze. In the robotic warehouse management example, the goal is that the robots pick the correct items, deliver them in the delivery bay without crashing into each other. But the way in which these agents learn to achieve that goal, it is different, is always the same. They only care about maximizing their reward. This is also the power of reinforcement learning. Regardless of your problem, the learning algorithm works the same. You don't need an heuristic, you don't need stuff like that, okay? Why did I mention expected? Well, nothing says that the way rewards are assigned, or even the ways in which the environment transition between states, must be deterministic. These things could be probabilistic, stochastic even, so depending also on time. So I must bring in expectations. Okay. the agents, if the reward function is probabilistic, so depending on the state there is a higher or lower chance to get a given reward, it is obvious that the agent can maximize the expected return. So the collection, the accumulation, the sum of rewards it gets during its lifetime in expectation, accounting for probabilistic oscillation. So how can we actually depict, let's try to be more clear about what do we need to do to define a reinforcement learning environment. Obviously, let's start with the easiest case, so the Markov decision process. How to define mathematically a Markov decision process? You need these ingredients. Let's call S a finite state of a set of states. What could it be? Well, in the maze example, the S could be all of the different positions of the agent within the maze. Those are all the states in which the agent can be. Do we agree? As always, raise your hand and stop me if something is not clear. I don't know, in the robotic warehouse management, every possible configuration of the items on the shelves and in the delivery bay. That is the state space. Okay. Then we need to define also set A, the finite set of actions that the agent can do. Okay. So for instance, my robot can move, let's imagine for simplicity to be in a discrete world, my robot can move at the front, at the back, at the right, at the left. For instance, not diagonally. Can it move diagonally? Okay, the action space is different. Are we in a continuous space? Maybe my action space is the direction of movement and the torque of my motor, of my wheels. Could be. Okay, so define the action space is another step we need to do. And obviously we need to define capital R that usually denotes the reward function. A function that does what? Given a state, an action, and a future state in which I will end up, give a number that denotes whether the action was good or bad. And the number can be any scalar value. This is the reward function. Were you in state S? Did you do action A? And so did you end up in state S prime? This is your reward, according to my reward function. That can be a deterministic function, a probabilistic function, could be a cascade of if then else rules, could be a continuous function. I want my robot to learn the optimal path toward a given target location. My reward function is a continuous function, okay, that has a minimum in the straight path. Could be, okay. And we need another ingredient, which is usually called T, that is the state transition function instead. How does the environment transition from state to state? And so this is another function that usually is probabilistic. So the output is a probability between 0 and 1 that tells you, given that the agent did this action in this state, what is the probability of ending up in this new state? That's the transition function in the most general terms, okay? The transition function can also be deterministic. Okay? It means that it only outputs 0 or 1. In the most general case, it can be probabilistic. By doing this action, the agent can end up in this state or that other state, randomly, according to some distribution. And then you need an initial state distribution. So basically, what is the initial state of the environment? In the maze, it could be that the agent is not always in the same starting location, but anytime you try the maze, the starting location changes. Again, so this distribution is a probabilistic distribution and not a deterministic function in general. Is everything clear? So these are all the ingredients to define a Markov decision process. And here basically is how we can depict graphically this process. The state at time t minus 1, okay, determines the reward in that state, so still time t minus 1, determine the action that the agent will do, because the agent will observe the state and decide an action. And then obviously the previous state is also linked to the next state, as is the action. Is that action that led me to this state. Okay? Whereas, by our very definition, all of these three contributes to deciding the current reward. Current state, the current action, the next state. Here I depicted 2 time steps to highlight what? The Markov property. State t plus 1 only depends on state t and on what happened in the first step. It doesn't depend on what happened before. If you, while brainstorming about how to model your environment, find out that you have a connection, okay, from a past state, it's not a catastrophic thing, it is not that you're wrong, simply you cannot model your environment as a Markov decision process. It's something else. Okay, that's it. Probably it will be more difficult to find a solution because we said that the Markov decision process is the easiest one, but it's not a catastrophe, it is not that you're wrong. Okay, simply you are in a different world. The Markov assumption does not hold anymore.